Hey everybody. Today we're talking about functions. A function is just a rule that takes values from one set, that we call the domain, and assigns to each one a value from another set. That's called the range. Functions are everywhere. For instance, the amount that you pay at a gas station is a function of the amount of gas that you pump. The population of the Earth is a function of time, and the maximum height attained by a bullet is a function of the angle at which the gun is fired. Now, there are many ways to describe a function. The simplest is just to make a table of values, the inputs along with the corresponding outputs, like so. Here, if we have an input of 1, this rule is going to give us an output of -3. It's very common to denote the inputs with the letter X and the outputs with the letter Y, although there's nothing particularly special about those variable names. You'll see others as well. Notice here that we have an output value, 2, that's repeated. That's fine. Multiple inputs can have the same output. However, it's not allowed for the same input to have 2 different outputs. Remember, a function assigns every input to exactly one output. Closely related, we can also describe a function with a list of ordered pairs, like this. Here, the input 1 gives us an output of -3, the input 2 gives an output of 5, and so on down the line. Frequently, we name functions with individual letters, f being the most common, f for function, and that lets us write things like this. We put the input inside parentheses with the letter in front, and then we put the output separately. These get read f of 1 equals -3, f of 2 equals 5, and so on. Now, in higher math, it's most common to define functions algebraically. We use a variable and then explicitly write out the rule that defines the function, like so. F of x equals x squared. For any input, we're going to square it to get the output. So, for example, f of 2 is 4, because 2 squared is 4. F of -10 is 100, because -10 squared is 100, and so on. The domain of this function is all real numbers because we can square any real number at all. The range, however, the list of possible outputs of this function, is only the non-negative real numbers. It's impossible to square any number and get a negative number back. Tiny bit of terminology here. The input variable, here x, is called the independent variable. It doesn't depend on anything at all. The output variable is called the dependent variable because it does depend on the specific rule that you're using. Here's an example. Evaluate the function f of x equals 2x squared minus 3x plus 1 at x equals 4, -2, and 1 plus h. Simplify the results. So let's start with 4. We want to find f of 4. In order to do that, we're going to look at our formula. Wherever we see x, we are going to replace it with 4. So 2 times 4 squared minus 3 times 4 plus 1. Then I simplify this a little, squaring 4, multiplying 3 times 4, and so on, to get 21. Similarly, to do f of -2, I am going to remove x from my formula and replace it with -2. Notice that I put parentheses around the -2 there. The entire quantity -2 needs to be squared at the beginning of that function. I'm not just squaring the 2 and then making it negative. Simplifying this out a little bit, 8 plus 6 plus 1 is 15. Finally, f of 1 plus h. So here I have a letter in there, some unknown, but the rule is exactly the same. I go to my definition of the function, take out the x's, and replace them with 1 plus h, the thing I'm plugging into the function. Again, I'm including parentheses to make sure that all of 1 plus h is being squared and that all of 1 plus h is being multiplied by 3. To simplify this, I'm going to FOIL out the 1 plus h squared, distribute the -3, then distribute the 2 through, combine the -3 plus 1 to get -2, And finally, combine like terms. Overall, I get f of 1 plus h is h plus 2h squared. We can represent functions visually with a graph. Inputs are measured horizontally, left and right, and outputs are measured vertically. So for example, this function that we saw earlier, defined by these 4 points, input of 1, output of -3, and so on, has this graph. The way that we plot these points is by starting at the origin, the spot where the horizontal and vertical axes meet. And then we count left and right until we get 1 unit to the right to get the x value of 1. And then we count 3 units down to get a y value of -3, to get to the point 1, -3. Similarly, for the point 2, 5, we count 2 units to the right, 5 units up, to get to the point 2, 5. A graph defines a function as long as no x value has more than one y value. For instance, here's a graph that defines a function. Let's call it f. Here, f of -1 is 0. If we go left 1 unit from the origin, we don't need to go up or down at all. F of 0 is 1. If we don't go left or right from the origin, we have to go up 1 unit. F of 1 equals 2, f of 2.5 equals 2, and so on. There's a simple visual test for whether a graph truly represents a function or not, and that's the vertical line test. To use the vertical line test on a graph, we check to see if there's any vertical line that ever intersects the graph at more than 1 point. If there's no vertical line that ever intersects the graph at more than 1 point, you have a function. For instance, here the graph on the left passes the vertical line test, but the graph on the right doesn't. On the right, there are many vertical lines that will intersect this graph at more than 1 point. A very common task is to take a function with an algebraic definition, like x squared minus x, and then produce a graph. Technology is a great help here, of course, but we don't want to have to rely on it exclusively. The single most important and basic way of graphing functions is just by plotting points. So, for example, with f of x equals x squared minus x, we can make a small table of some of the values and their corresponding outputs. When x is -2, f of x is 6, and so on. And now we can plot these individual points on the graph. -2, 6, -1, 2, 0, 0, and so on. Here we see the result. I've graphed these 6 points. Of course, I could add many more points to this plot. If I want to get a better feel for this shape, I could do x equals 1/2, for example, or x equals -3. Once I've got enough points plotted, I can get a good impression of the shape of the graph just by connecting the dots, potentially in a smooth way, like so. This is roughly what the graph of f of x equals x squared minus x should look like.